All right, hello everybody. It's a Friday morning lecture for thermodynamics that I'm recording here, and the midterm number 2 exam has just completed, and it was a bit of a whirlwind, I have to tell you. So I want to talk a little bit about the midterm exam. I've already gotten some emails from a number of you with concerns about not finishing the exam. So I know I talked, I think, in the last video lecture about how I was not expecting that people were going to finish the exam and etc. Though I think maybe some people expected that maybe they would. Um, so let me explain my philosophy now, and I also send out an announcement a little bit later. The idea was that this exam was supposed to be kind of long and hard so that there was limited chance for collaboration. And since it was an open book exam, I didn't want people sort of digging through and looking for specific examples that matched the problems. So the idea was to see how far people got, and you got as far as you got, and then I would grade the exam on a curve. So that's what I'm intending to do. So don't if you're like really still bummed out about the exam and really stressed out about it, please don't be. I will go through it and grade it with the TAs, and we will do our best to be fair. And we will curve the exams and make sure that that people get the right appropriate credit for the work that they did. Okay. I know that it might have been a little bit stressful. I know it was stressful for me actually just monitoring the whole thing. So so hopefully take some deep breaths. It's gonna be okay. We'll give you feedback on the exam. We'll try to do the grading the best way possible and try to get back, some semblance of order here. All right, so that's the exam. Let me just cover it real quick, okay? And I'll cover it again next week. But yeah, so the exam covered, as I have it here on the screen, it covered a problem here where we had short answer word problems. We had a problem with a power cycle where I actually had made a typo, which somebody picked out at the very end, where this was 300K reservoir, and I said heat exchange with the ambient at 298. These are supposed to be both 300K, so I made a mess up there, so I really apologize about that. I think a lot of you kind of understood what was going on. I've looked through some of the exams already, and there was some uh, there was some understanding there. Hopefully, so number 3, this one was an easy one. I thought people, we did the feed water heater example in class with the water and the feed water heater. This is exactly the same as that, except that it's a little bit mixed up in terms of how the stuff. But it was that one. I thought this one was sort of a giveaway. Number 4, most people didn't get to. Number 4 is a hard problem. So I expected that people would have trouble with this one. This was the one that people would I'm hoping that people got through 1 through 3. And then number 4, you just did as much as you could. Okay. Number 4 was hard as a transient problem that involved a steam flowing in a pipe, and then the steam going into a piston, which then was locked and then expanded. So that's kind of a tricky situation. We definitely covered this material in class, though. What you needed to do to get to this is difficult. Here's what I'll do: is I'll grade the exams with the TAs, and hopefully next week, and then I'll publish a video lecture on going through the solutions, and that way you have an idea as we go towards the final, sort of what we expect, that and how you put these things together. Okay. All right, let's move on from the exam and start talking about with the new material. So what we have to do today is finish up chapter 6. I really just want to be done with chapter 6 so that Monday, fresh start, we can start on cycles and start talking about cycles. We only have a couple weeks left of the semester. So there's Lola's upset about the exam too. Come here, Lola. Yeah, she was stressed out too. Yeah, see, she's stressed out right now. Okay. So, all right, so let's see. Let's look at the survey from last time. So the survey from last time is for an incompressible substance, the change in entropy for an isentropic process. As you remember, isentropic processes are adiabatic and reversible. Is dependent on, choose one, Only temperature. So temperature and pressure would have been the right answer if we were talking about a gas, like an ideal gas. But when I said incompressible, I mean a liquid. And for a liquid, it's only a function of the temperature. Okay? Um, an isentropic process, so there shouldn't be any heat transfer. It's adiabatic for an isentropic process, and pressure only is not correct. So yeah, most people got this one correct. So let's move on to new material here. All right, one thing I want to cover first and get this out of the way is to talk about these tabulated values of PR and VR. So PR and VR are for talking about reversible. Oh, sorry, let me just get rid of this and get rid of these things. All right. So what we're talking about is a process where S1 equals S2, so a reversible process. Okay, reversible process with no heat transfer. So that'd be an isentropic process. S2 equals S1. So if we want to find out for an isentropic process how to calculate the pressure change or the volume change, we can essentially, this is based on the TDS equations that we developed last lecture. So P2 over P1 equals PR at T2 over PR at T1. Okay, so these are just like a pressure ratio. So like what you can do is you can use this equation right here and use the tables to determine what the pressure ratio would be for an isentropic process. It's pretty straightforward. We're going to do an example that uses this a little bit later. So I just want to let you know. So you can use this S naught thing and look up S naught with a pressure correction, which is what we've been doing so far. Or you can use these PR and VR, and you can look at in the air tables, for example. So this is only for ideal gas, or for any ideal gas. For the air tables, you can look up PR and VR for isentropic processes and understand the pressure and volume ratios very easily using those tables. Okay. So yeah, we'll do an example of this. It's pretty easy to use and maybe is like a little of a shortcut for if you want to do an isentropic process. Otherwise, you can just use the TDS equation on the ideal gas entropy change that we were using before. VR is the same. So V2 over V1 for an isentropic process equals V2 over V1. So then we'll do an example of this. But so this is for only for air for this table and for ideal gas and for isentropic process where S2 equals S1. Okay. All right, we already covered this. All right, so I just wanted to get through that stuff last time. And we talked about the isentropic relations, T2 equals T1, P2 over P1. So that's always really nice to use for an ideal gas. We didn't do that in the exam, but you can expect that we'll do something like that in the future. I do have to give you some homework assignment over the weekend. I'm sorry. No rest. We have to keep moving. All right, the next thing I want to talk about is turbine efficiency. Okay, turbine and compressor efficiency, and we talked a little bit about this in one of the example problems that we did. So for an isentropic turbine, essentially we know that we can simplify the energy equation to what you see here. For any turbine, for adiabatic turbine, we can get rid of the Q term, which is what we've done here, and leave the work term. And so essentially we have work equals H1 minus H2. So I think actually in the in the exam we had Q, but we dropped off these guys and we dropped off the potential and kinetic energy, and then you ended up with a work term equals H1 minus H2. Okay, and so this is the first law. Now for an isentropic turbine, we have the second law, entropy balance. So the entropy balance is 0 because it's steady state. So ds CV dt equals 0. Adiabatic, right? So it's isentropic, so this goes to 0. And then essentially what you have for any turbine is the rate of entropy reduction over m dot equals S1 minus S2 is greater than equal to 0. So when you have a reversible turbine, which is the isentropic case, you have S1 equal to S2. So if you look at this diagram here, this is the Mollier diagram, the H and S diagram. You can see that for an isentropic turbine, you have S, so you have 1 to 2S, which is the expansion from 1 to 2S, and then you have the actual, which is 1 to 2, which is in the case where you would make entropy. So the state labeled 2S in the figure would obtain only in an isentropic expansion from the inlet state to the specified pressure. So we would have 2S only in the case of internal irreversibilities. So the maximum theoretical work that you can make from the turbine would be H1 minus H2S. The work, I mean the specific work, so kilojoules per kilogram, would be H1 minus H2S. That's the maximum amount of work you can develop in a turbine. Similarly, for a compressor, we go the other direction, right? So you'd be compressing, but similarly, the lowest amount of work you would put in for a compressor would be H1 minus H2S. Okay, so therefore we can define an efficiency metric, which is sort of what we did in an example like last week. So you can have this work over the work ideal. So like the actual work would be H1 minus H2 for an adiabatic turbine, and then the theoretical work would be the work over the isentropic work over mass flow rate, which would be H1 minus H2S. So this would be what we call the isentropic efficiency. Sometimes people call it the first law efficiency of a turbine, but it's nice to call it isentropic efficiency because it's not in over out. It's sort of like the amount of work versus how much work would be actually you'd get out of the process. Okay, so here's an example. So water vapor enters a turbine at 5 bar and exits at 1 bar. So we have work given 271 kilojoules per kilogram of water. And then we applied, this is the equation number in the book. If we apply that isentropic efficiency equation that we just developed, we can look at the table and find out this is superheated at state 1. And then S1 equals S2. So we can get S2S equals S1, and we can interpolate to get an H2S of something. And then we know what the actual work is. It's 271 per kilogram of water. So, it's 271. And what you end up getting is an efficiency metric of 75%. Okay, we'll do an example of this one to show you how it works. Same thing goes for the compressor and pump. So compressor and pump have the same equation essentially. You've got work equals H1 minus H2. Just that you're going to have work going in, which means that its work is minus. Okay. You have the same deal. You have S1 equals S2, and you have, this is like the same slide, except that you have a compressor on this figure. So 1 to 2. So remember, before it was 1 on the top and 2 on the bottom. Now it's 1 on the bottom and 2 on the top. So for 1 to 2, you're generating entropy, and 1 to 2s, entropy stays constant. Okay. So essentially, it's the same thing. It's the exact same thing, except that when you have the isentropic efficiency, which is here, isentropic efficiency is the ideal over the actual. So the isentropic over the actual. So it's the inverse. It's the inverse for the compressor because it's the ideal amount of work, which is lower than the. So you want an efficiency metric to be between 0 and 1. You can't have the minimum amount of work you can put in is the isentropic work for a compressor or pump, and the actual work is always going to be higher. Okay, so that means that this is going to be a ratio below 1, between 0 and 1. Okay, so the pump efficiency is defined similarly. So I believe there's an example here. Yeah, I have an example here. So let's do this example, and this is going to be great because it's going to use both. Let's see, air enters. You can use the PR as well as the isentropic efficiency stuff. All right, so let's get here. Let's get my iPad going here. And then, okay, so let's get to the right thing. Here we go. So air enters the turbine of a jet engine at 1190 K and 10.8 bar and expands to 5.2 bar. The air then flows through a nozzle and exits at 0.8 bar. Operation is at steady state and the flow is adiabatic. The nozzle operates with no internal irreversibilities, and the isentropic turbine efficiency is 85%. The air velocities at the turbine exit and inlet and exit are negligible. Assuming the ideal gas model for the air, determine the velocity of the air exiting the nozzle. Okay, so it's a coupled problem, right? But they're giving us an isentropic efficiency. That's what makes this problem interesting. And then so then we can figure it out. All right. So let's do this. All right, Lola, you're gonna have to go somewhere else so I can write. There you go. Okay. Now I got cat hair on my my iPad. Okay. All right. So let's it's shedding season. All right. So now let's get here. All right. So what are we gonna do here? So first things first is we're gonna write the known. Somebody asked me this question, as they always do before an exam. Should we use the known and find in the exam problems? I say yes, because that's what we've been doing. So default, do what we've been doing. I think it's helpful. For one, it gets your thoughts straight on what you're trying to do. It makes you read the problem. Sometimes people miss things in the problem if they don't write it down. And it just gets your thoughts straight on what you're going to do, right? So it's just kind of part of the normal engineering procedure. All right, so anyways, what's known is that we have a turbine plus nozzle with air as working fluid. Okay, what we have to find in this case, what we're finding in this case is the exit velocity, right? So we're finding v. Well, we're gonna call it v3 because there's two components, right? So if we make some assumptions here. So some assumptions here. First, we're gonna say first is gonna be steady state. 2, we are assuming that q dot equals 0 adiabatic, and that work dot equals 0 for the nozzle. Obviously, the turbine has some work. 3, I think we're going to assume ideal gas. 4, we're going to neglect delta PE and KE. I think we're going to neglect KE from the, except, so this one is except at the nozzle exit. Okay, and then we're gonna, 5 is going to be the nozzle has no internal irreversibilities. Oops. Okay, no internal irreversibility. So a lot of assumptions in this problem. All right, let's make the diagram. Okay, let's make the diagram. So to make the diagram, it's going to look like this. There's going to be a turbine. Okay, some turbine. Call it T. You have stuff coming in, and it's a radial flow turbine. And then we're going to have a nozzle. So we're going to have some sort of nozzle. Looks like this. Imagine like a fighter jet or something. It's got a turbine and a nozzle, right? So we're going to call this state 1, call this state 2, and call this coming out state 3. It's a converging diverging nozzle. It doesn't matter. We could make a nozzle. We could have made it just like a tapered down or something like that. It's probably a little bit confusing to make it a converging diverging nozzle, but okay. What we're given is that, so P1 equals 10.8 bar, and T1 equals 1190K. State 2, we have P2 equals 5.2 bar, and P3 equals 0.8 bar. It's a little under expanded. Okay, we're going to make ourselves a TS diagram just to explain this thing. And we got different pressures, right? So I'm just going to draw the pressures that we're operating. So we have 0.8 bar, 5.2 bar, and then we have, what's the last one? 10.8 bar. Okay, so now we have two different processes, right? So we have 1 to 2, 2 to 3. So 1 to 2 is expanding through the turbine. The turbine's making some work. I assume it's making some work. Work is coming out of this thing, positive. And then what we're going to do is we're going to take the, so from state 1 at 10.8 bar, we're going to expand it down to something here. So 2. State 2 is somewhere down here, right? It's an 85% isentropic efficient turbine. So, oops, let me get myself moved out of the way here. So it's an 85% efficient isentropic efficiency turbine. And so there's going to be a line here this is going to be our 2s. So our isentropic idealized turbine. Ooh, that doesn't look straight on the screen here. It looks straight here, but it doesn't look straight on the screen. Okay, 2s. That's better, right? That looks straight. Okay, and then from 2 like this, and then we're going to have from 2 to 3 is actually no irreversibility. So we're going to assume that this is straight. Ooh, it actually made a straight line, didn't it? How do I do that? I don't know. That was cool, though. I should figure that out. I'm really having a hard time making this look straight. All right, that's pretty good. 3 is there. Okay, so this is what we have. Okay, this is the kind of TS diagram that we're talking about. We don't know any of the temperatures, I don't think. Oh yeah, we do. We know T1. So T1 is 1190. We don't know T2, T2S, or T3. We don't know any of those guys. All right. All right. So we have to figure that out. But we do know that we have 85% isentropic efficiency. All right. So let's do continued here. So now let's put our analysis here. So in our TS diagram, we put as much as we could in there. As you get good at these, and as we do this thermodynamic cycles, you can start making the TS diagram right away. You don't have to make it as part of the problem later, right? You kind of deduce what's going on based on what's happening in the problem statement. And so you know how to essentially to draw the diagram roughly right from the beginning, okay? And that's what I kind of would hope you do. So this is a nozzle, right? And then we'll draw our diagram. So essentially we can make the whole thing our system. I don't know if we're going to do that. We're probably going to make individual systems. We'll probably have 2 control volumes. We have CV1 and CV2. I imagine we're going to analyze them piecewise. Okay, so let's find state 2. So let's consider control volume number 1. Okay, considering control number 1, let's just break out our isentropic efficiency. So the A to T, which would be the isentropic efficiency of a turbine, would be H1 minus H2 over H1 minus H2S. Okay, so that's the isentropic efficiency of a turbine. So then we're going to find what H2 is. H2 equals H1 minus A to T H1 minus H2S. All right, so since we have the temperature at state 1, we definitely know what H is, right? Because we can find that pretty easily. All right, to define H2S though, it's going to be a little tricky. What we're going to do is we're going to use the PR function. So to find H2S, we're going to use the idea that PR at T2S. I don't like this. At 2S is equal to 230, which is the, well, we'll just say PR at T1 times P2 over P1. Okay, so that's what we're going to do. So that's the relation that we just saw in the slides that I showed you. Okay, so now what we're going to do here is we're going to use the table A22. So table A22. And we're going to use table A22 to find out what's going on here. So PR2 is equal to, or PR2S is equal to 230. So that's PR at T1. So PR at T1, we'll just say at 1. PR1 equals 230. And there's no units on PR because it's a ratio. So there's no units on that. But there is units on the pressure. There's just no units on PR and VR. And then, so we know the pressure ratio. So we can find out what this is. So if we look it up, we can just sort of interpret that T2S, oh, I'm sorry. I will go back. I went a little too. P2 is equal to 230 times the ratio of 5.2 over 10.8. Okay, and this is equal to 110.8. And so this is PR2. So if we look at this at the table, we're going to get H2S is essentially equal to 1038 approximately, and T2S is approximately equal to 992K or 993. K. Okay. All right, so we have 990. This is kind of poorly written. All right, 993K. Okay, now, so then we can find H2. So H2 actually, so we don't have to look that up on the table. We just use the isentropic function, and we get H2 equals 1266, which is, I said, what H1 is. So H1 equals 1266 minus, 1266 minus 0.85, which is the isentropic efficiency, times 1266 minus H2S, which was 1038. Okay, and this ends up giving us something like H2 equals 1072 kilojoules per kilogram. Make sure I put my units in here. Okay, kilojoules per kilogram. So that's H2. So now interpolating, we can find T2 is equal to about 1023, 1023K. And PR2 at is equal to 124.7. So we have PR2 now. So we have PR1 and PR2S. So PR2S is 230. I'm sorry, 110.8. Right. But now PR2 is actually 124. Make sure I get this right. So this is PR2S. And then up here, PR2S is 110.8. And PR2 is 124.7. Okay, and now we can find out for the nozzle for control volume 3, or I'm sorry, control volume 2. From state 2 to 3, we have PR3 at which is at the isentropic, because it's an isentropic nozzle, which doesn't really happen, right? And you don't really have an isentropic nozzle, but okay, so we have an isentropic nozzle. PR at T2, and then P3 over P2. So using the PR function again, we end up getting 124.7, which is PR2, times the ratio of the pressure, which is 0.8 over 5.2. And this ends up getting us a PR3 value of 19.191 from the table. And then we can interpret that as H3 equals H3S, which is the isentropic enthalpy, which is 634 kilojoules per kilogram. And the T3 is equal to 625.6. All right, so now we know what that is. Now, the only thing we have to do now is we have to figure out what the velocity is, okay? So for that, we're going to use the first law for control volume 2. So 0 equals Q dot minus W dot plus M dot H1 minus H2. And we're going to skip the, we're going to skip the potential energy, and we're going to go, we'll put a square bracket here, and we'll go V2 squared over 2 minus V3 squared over 2. Oh, I'm sorry, this is supposed to be 2 and 3. And then, based on our diagram, all right, so but this guy goes to 0. We assume this is 0. We're assuming the kinetic energy is negligible at the inlet to the nozzle. But the outlet to the nozzle, it's something. Okay, so continued now. All we have to do is find this. So V2, so this guy goes to 0 in the nozzle. This guy goes to 0 in the nozzle. So really all we're left with is V2 is equal to, and the M dot drops off because it's divided by 0. So the V2 equals 2 times H2 minus H3S, okay? And then this ends up being 2 times H2, which we already know is 1072 minus 634. And then, of course, we have to do this 1,000 correction. Usually we have to do 1,000 to get the kilojoules, to get it into joules per kilojoule. And then this ends up being, to get us to meters per second, so 935 essentially 936 meters per second. Okay? When you're doing the velocity stuff, you got to make sure you have that factor of 1,000 in there, or else you're going to run into trouble with the kilojoules. All right, so that's the answer. So now we've kind of shown that this is really useful. This PR is really useful for isentropic processes. So it's sort of a way to sort of easily use the tables for isentropic processes. And then since even though the turbine itself wasn't isentropic, we can use the isentropic enthalpy and temperature to solve then for the real one using the isentropic efficiency. Okay, so hopefully this example should give you a good sample of what to do. Okay, so let's move on with our slides now. See how much time we have to go through the rest of these. All right. Next thing I want to do is talk about heat transfer and work in internally reversible steady flow. So consider a one inlet, one outlet control volume in steady state. Okay. So we have a lot of things like this, compressors, pumps, nozzles, valves, other things like that. The objective is to introduce expressions for the heat transfer rate and the work rate in absence of internal irreversibilities. The resulting expressions, they do have important applications and something that we want to examine. So the agreement of the discussion on energy transfer by heat to a closed system doing an internally reversible process, we have this, so reversible means the sigma goes away, right? So we have Q over M dot, so this is some Q of the CV, equals 2 to 1 TDS, right? So where the internally reversible subscript shows that the expression applies only in the absence of internal reversibilities, i.e. when sigma is 0, okay? As shown by the figure, when the states visited by a unit mass passing from inlet to exit without internal irreversibilities are described by a TS diagram, the heat transfer is the area under the curve, which we know. Okay. Now, neglecting both kinetic and potential energies, an energy rate balance for the volume is for the control volume reduces to the following: one inlet, one outlet. You'd get rid of kinetic and potential. You end up getting work equals the Q plus H1 minus H2, right? And then you end up putting the Q in from the second law entropy balance into the first law, and so you get work, a little w, so work over m dot equals power over m dot is equal to the integral of TDS plus H1 minus H2. So entropy and pressure changes therefore related by the TDS equation, and so what we can do is integrate this for the exit, and we can get the following: that the TDS is equal to H2 minus H1 minus VDP, and when this relation is combined, we end up getting the following expression. For an internally reversible process, the work is equal to the negative VDP. So this is confusing because we said very early on in the class that work equals PdV, not VDP. However, for an internally reversible process, steady flow process between the single inlet and outlet, the work, internally reversible work, is equal to VDP. So I think this is really important, especially when we get into vapor power cycles, which are the Rankine cycle, which we'll talk about. So this is an important feature that we need to understand. As shown in the figure, when the state visited by unit mass passing from inlet to outlet without internal irreversibilities are described by a curve on a PV diagram, the magnitude of VDP is shown in the area behind the curve, to the left of the curve, so the integral of PdV. So a compressor, okay, here's an example. So a compressor operates at steady state with natural gas entering at P1V1. The gas undergoes a polytropic process described by PV equals constant and exits at higher pressure. Ignoring the kinetic and potential energy effects, evaluate the work of mass flowing. if internal irreversibilities were present, would the magnitude of the work unit per unit flow of uh, of natural gas be less than, same as, or greater than determined in part A? All right, so let's see. So with PV equals constant, the internally irreversible. So we assume that it's polytropic, but it's still internally irreversible. That way you can use this work equals negative PDV. Now notice that it's not adiabatic, it's not isentropic, but it's internally reversible. So assuming that there are no internal irreversibilities, then we can use this equation. So then we can use negative VDP, and we end up getting here that solving the equation, solving the integral, essentially VDP, we end up getting the following for the polytropic process with n equals 1. Okay, we could do this for a number of different work things, and probably if we were sneaky, we could probably end up getting this the same equation that we got before for work. Okay, the minus sign indicates that the compressor requires work input. Okay, left for further discussion. Okay, so let's do an example of this. Okay, I don't want to get hung up on the VDP thing. I just want you to know that with VDP, it's the integral of VDP for an internally irreversible process, a control volume process. It's very specific when you can use that equation. Okay, only for those types of processes. It's a little confusing, but it's definitely handy when it comes to talking about internally irreversible pumps and compressors, which we'll deal with when we deal with the Rankine cycle and other cycles later. So that's why I'm introducing it. Okay, I don't want to confuse you, but we definitely could use it and will use it in a lecture or two when we talk about that. Okay, so let's do an example. I have one more example to do, and then we can quit for the day. Oops. I guess maybe I'm not here. Let's see. Okay. So example 2, here we go. So a pump operating in steady state receives saturated liquid water at 550 degrees C, saturated liquid water. So that means we're at the left part of the vapor dome, right? And a mass flow of 30 kilograms per second. The pressure of the water at the pump exit is 1.5, so we pump it up from, it doesn't say what the inlet pressure is. If the pump operates with negligible internal irreversibilities and negligible changes in kinetic and potential energy, determine the power. So did we say it has no, operates with negligible internal irreversibilities. It's a frictionless pump. Okay. Wow. Cool. Okay. So let's do that. So it's a pretty simple problem. So let's just do it. So known, we have an irreversible pump with water. Okay. With the properties known, we're supposed to find the power required. So we're supposed to find W dot, big W dot, which is power in kilowatts. Okay, assumptions. Okay, so the assumptions are that we have 1, the control volume, so we have a steady state. 2, we're going to assume that we have no kinetic or potential energy changes. And the third one and last one is that it's irreversible, internally irreversible. Okay, the diagram looks like this. We don't need to make a TS diagram for this one. I don't know, I just draw it like a pump like this. So I say it's a pump like this. We have water coming in and water coming out. So this is the universal symbol for pump. Okay, and this is my control volume. We have some work going in. Actually, we always draw work going out, right? So this could be negative work. And there's no Q, right? Because it's adiabatic, I believe, right? No, we didn't say adiabatic. We're just trying to find we're just trying to find the reversible work. So for irreversible, internally negligible. So we're not going to say it's irreversible, it's reversible. Okay. Well, it's been a long day. Okay, 4 is that we're also going to assume that V equals VF. at the function of temperature, not a function of pressure. So we're just going to use the VF from the table, which is what we do usually with liquids, okay? I still don't like this very much at T, okay? As a function of T. Now, all right, so what are we going to do? So A, we're going to assume that we have the work little w is equal to negative V P2 minus P1. This is for a reversible pump. Okay? It doesn't mean adiabatic, it's just reversible, okay? So P1 equals P sat at 50 degrees C, which is something like and V1 equals VF at 50 degrees C. And so we'll use table A2, I believe, to find that out. And so if we just solve this thing, so we have, so then we have volume is, and then we have work equals negative V, which is 1.021 meters cubed per kilogram, times 1.5. So what do we know the pressure? We know the pressure is 1.5 megapascals, right? So P2, so 2, P2 equals 1.5 MPa. And we know P1 is because P1 is P sat at 50 degrees C, right? So that's pretty straightforward. So this is 10 to the third kPa minus 0.1235 times 10 squared, or 1 over 1,000. And then we're going to end up getting here a negative, make sure to pay attention to the units, 1.51 kilojoules per kilogram. And then so if we know with the reversible work then is that we can calculate it, the actual work. So this is little w. So the big W dot is equal to 30 times negative 1.51, which is the kilojoules per kilogram, right? So then we end up getting kilowatts. Excuse me. Okay, so then we're end up getting 45.3 kilowatts for our final answer. All right, so just to go back, so this is from table A2. So table A2 is here, and then this is the temperature table for water, and that's where we get these items here. And I think these are right. I think this is right. 10 to the third. I think the units are right, but I think this is wrong. Just gonna make sure this is right. Let's see. Do this in pascals. No, we need the 1 over 1,000 here. Okay, so that's. I'll have to check my units later, and I'll put the right units in there. I'm pretty sure that's correct, though. I think it might be something screwed up in the solution. But anyways, it's a pretty simple problem. This is the key equation here, and this is, make sure we just know that this is for an internally reversible pump only, right? If it was not internally reversible, we would not be able to use this VDP equation. Okay, just remember that, and we'll deal with this later when we are doing more problems with the cycles. Okay, especially for the Rankine cycle. All right, so that does it for chapter 6. We'll continue to review this material and keep on going through it. We're going to keep using it. So hopefully, if you have any questions, please let me know. And if it's a challenge, or you want to know something more that I'm not covering, please let me know. Also, the book, of course, is there for your reference that you can use. Okay. With that, have a restful weekend, and look forward to seeing you again on Monday. Talk to you later.